And hello and welcome to lesson 22-4 practice. Now you'll notice that the screen looks a little bit different. The practice in the book has very limited space, so I'm not going to be able to kind of capture all of the work that I typically do because there's so little space. So there's going to be a lot of erasing and deleting, so just find the parts of the video that you actually need. So let's take a look at lesson 22-4 practice on page 316. Make sure you have your graphing calculator handy because we're definitely going to be utilizing that here. Or what I'm going to be doing for the most part is using Desmos. So it says in item 8, angle X is an acute angle in a right triangle. What measure of angle X makes each statement true? Round angle measures to the nearest tenth. So before we go any further, I just want to make sure it's clear that these are all separate problems. We're saying if the cosine of X is 0.59, what is X? If this statement is true, what's the measure of angle X? And likewise, for all of these examples in item 8, if, for example, B, if the tangent of X is 3.73, what is the measure of angle X? If that really is the ratio of the opposite side and the adjacent side of angle X, then what is the measure of angle X? Now, we are going to utilize very heavily our scientific or graphing calculators for this. So I will remind those that actually do have a graphing calculator. I'll show you how to do this here. Let's clear that off. So what I want to reiterate on 8a, and I'll do that out here, is if the cosine of X really is 0.59, then, and this is the ratio of the side that's adjacent to that angle X compared to the hypotenuse of a triangle that has that angle in it. This is the ratio, and a ratio is nothing more than a fraction. And another way to write a fraction, there you go, it's a decimal. So if this really is true, then the inverse cosine of that ratio should give us the measure of X. So the inverse cosine of 0.59 should tell us the measure of angle X. So let's take a look at that on our graphing calculator. So the inverse cosine, notice cosine is right here kind of towards the middle. The inverse function is right above it. So to access anything in yellow, we're going to hit second and then cosine. And the inverse cosine of 0.59. And it tells us 53.84, and it says round to the nearest tenth. So the 4 tells us to keep that 8 where it is. So X will be, and I would probably encourage you to write the measure of angle X equal to 53.8 degrees. It's a pretty simple concept once we know how to use the calculator, but let's just make sure we understand the context of this idea. So let's look at B. If truly the tangent of X is 3.73, then the tangent inverse of 3.73 should be the measure of angle X. I'll go and provide the measure of angle X from A right there. So now we're going to take the tangent inverse of that ratio, 3.73. I'm going to show you once again on the graphing calculator. So tangent is here. So to access the tangent inverse, we're going to hit the second key in yellow, and then the tangent key, and then simply key in the ratio, which is 3.73. And it'll tell us that it's 74.99. Here's a little trick to rounding, or it's a little tricky here, because this 9 tells this 9 to round up to 10. Well, this doesn't just become 0, it actually rounds this up a tens place. So this will actually be not 74, but 75 degrees. So rounding to the nearest tenth, we actually find that the measure of angle X is 75 degrees. So get in the habit of actually writing this proper notation, because that's what we're finding. We're finding the measure of an angle. So on item C, we are told that the sine of x is 0.87. So therefore, the inverse sine of 0.87 should be the measure of angle x. So I'm actually going to take this opportunity now and show just those that are using Desmos how to, again, use the inverse function on Desmos. So we're going to take the sine inverse of 0.87. So I'm going to go to my Desmos tab, go to functions, and then I'm going to key in the inverse of 0.87. And they said round to the 10th, so the 5 in the hundredths place tells the 4 to actually round up, so it'll be 60.5 degrees. So I'm going to keep doing that. My apologies. The measure of angle x, based on this ratio, is 65 degrees. Now, at this point, I think a lot of us are hopefully getting the hang of inputting this in the calculator, and that's really what they're trying to make sure we know how to do. Oh, I believe it's not 65. Let me check that. It's 60.5. Excuse me. So let me fix that before there's too much confusion. It's 60.5. Get a little ahead of myself sometimes. So what I would encourage you to do at this point is rewrite these statements so we're understanding the context of the work, and then continue solving for angle x in item D, E, and F before playing through. Okay, here, hopefully you've taken an opportunity to kind of continue through the practice, and here are the 3 trig functions I just used for items D, E, and F. The tangent inverse of 0.18, the cosine inverse of 0.02, and the sine inverse of 0.95. If we take a look at our answers, hopefully we got the measure of angle x for D was 10.2 degrees, the measure of angle x for E was 88.9 degrees, and the measure of angle x for F, 71.8 degrees. And here's all the work hopefully we're showing. Now, I do want to kind of take a moment and just, again, put this idea in context, because we could just kind of get through the motions, not even understand what we're doing here. So this said that the cosine of x is 0.802, and the measure of that angle is 88.9. So just to put it in a little context, so we have a right triangle. We know it's a right triangle because we're dealing with right triangles. And it's interesting that I'm drawing it this way, because we're saying that in reference to angle x, the adjacent side when compared to the length of the hypotenuse is actually really, really small. Look at this number compared to all these others. Now, this is pretty close, but for the most part, this is actually a relatively small number. So we're saying that the length of the adjacent side is very, 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 very small compared to the length of the hypotenuse. And go back to what x was in this case. It was 88.9 degrees. So we already know that if it's a right triangle, one angle's 90 degrees, and therefore the other angle also has to be nearly 90 degrees as well. And so the reason I drew this triangle the way I did is because, and I know that's pretty awful, but just bear with me. We already know that this angle is 90 degrees. Well, the relationship of the adjacent side, and we'll just assume this is the adjacent side when compared to the hypotenuse, is actually very, very small. That's why this angle right here was nearly 90 degrees itself. Now, obviously, it couldn't have been 90 degrees, otherwise it wouldn't make a triangle. But the adjacent side to this angle, and we're calling this vertex x, because that's the angle we were looking for, the adjacent side to it had to be very, very small when compared to the length of the hypotenuse, because look at the ratio. 0.00 or 0.02 is 2 100ths. It's very, very small. It's like 2 pennies out of 100. It's very small. And so that's what I'm just trying to stress here with these ratios. is this ratio right here, 0.02, represents the length of the side adjacent to that angle when compared to the length of the hypotenuse. And it would create some triangle that looked kind of crazy like this. So just kind of keep it in context as we move forward. Now 9 says solve each right triangle if possible and route your measures to the nearest tenth. So they're implying that there's a possibility here that we can't solve one of these triangles. Remember, solving the triangle means finding any unknown measure. So for 9A, we definitely need to find the measure of angle A, we need to find the side BC, and we need to find the side AC. And it looks like we have enough information because what we said back on item 6, if we have one angle measure and a side, we should be able to find all the other parts, unknown measures. So we know that angle B and angle A have to be complementary angles. So what can I add to 49 degrees to give me 90 degrees? Hopefully you said 41 degrees. So the measure of angle A has to be 41 degrees. Now, because we only know one side of this right triangle, we definitely can't use the Pythagorean theorem at this point, but maybe further down the line once we find another side. So based on what we were given, let's say we're going to solve for AC first. Find the missing side AC. And that side AC is opposite of the 49-degree angle. So we're looking for the opposite side, and we were given the hypotenuse. So we're going to use the trig function that utilizes the opposite side and the hypotenuse, which would be sine, because the definition of sine is opposite over hypotenuse. So the sine of that 49-degree angle should equal the opposite side I'll call it lowercase b. Typically in a triangle, whatever opposite of the angle, notice the angle is named with the capital letter, typically opposite of that is the lowercase form of it. So we'll say sine of 49 degrees is the opposite side, which we're calling lowercase b, the unknown measure, over the hypotenuse 27. Now, there is a way, depending on what calculator you have, there is a way that we don't actually have to get the decimal approximation of sine of 49 before we move forward. So I'm actually going to show that. So we're going to rewrite this as a ratio on the left side, sine of 49 over 1, and we're going to do cross multiplication. So I'll get b equals 27 times the sine of 49. Now, previously, we put sine of 49 in the calculator and gave a decimal approximation of it, and then did the cross multiplication. I'm going to show you here how you don't actually have to get the decimal approximation first. You can, especially if you round it far enough, like the thousandths place, it shouldn't mess up our final answer at all. But I just wanted to take this opportunity to show you how you didn't have to change this to a decimal just yet. So using our graphing calculator, we're going to take 27 times the sine of 49. Close parentheses. And we get 20.37, which they told us to round to the nearest tenth, so that's 7. We'll round the 3 up. Those of you using Desmos, I'll show you how to do the same with the Desmos calculator. So let's get rid of these. So 27 times the sine of 49. And there's the answer as well, 20.37, which again, the 7 rounds the 3 up to a 4. So B, hello, keep doing that. B is approximately 20.4. So the length of this side AC is 24, or 20.4. Now that we do have 2 of the sides of a right triangle, we can use the Pythagorean theorem to find this third side. So this might be a great opportunity to remind ourselves how to implement the Pythagorean theorem. So in this right triangle, the side I'm looking for is just one of the legs. So it could be A or B, but since we've already called this side B, we'll say that we're solving for A here. As long as 27, this length of AB, is the hypotenuse C. So we'll take 20.4 squared plus, I guess I'll do a little bit backwards. So it's a squared plus 20.4, which we call b, equal to c squared, which we already know what c is, 27 squared. So let's use our handy dandy calculator to square those. 20.4 squared is 416.6. 27 squared is 729. We'll subtract 416 from both sides, or 416.6, and we'll get a squared is equal to 312.4. Last but not least, to find a, not a squared, we're going to take the square root of both sides. And a is approximately, my calculator says 17.67, so the 7 tells the 6 to round up to a 7. So we have now just found all missing or unknown measures of this right triangle. Therefore, we have just solved the right triangle. Now let's take a look at item B. Notice the information that we're given on item B. We're told not just the measure of one acute angle, in this case angle Y, we're also told the measure of our other acute angle, which we could have found that pretty easily because we know these two angles do have to add equal 90 degrees. The problem here, however, is that we actually can't find any sides because we weren't given the measure of one of the sides. Right? If we wanted to say, let's say we wanted to find the length of YZ using a ratio, one of our trig ratios. Well, a ratio compares two sides. And we can't write, for example, if we wrote the sine of 72 degrees would be the length of YZ over the length of X, the length of YZ over the length of XY, Notice we don't have either measure of these two segments, therefore we're not going to be able to solve for either one of them. So this goes back to what we said in item 6, what it requires for us to solve a right triangle based on what we're given. And so A strongly tells us that if we're given one angle and one side, we can solve the right triangle. B, if we just know angle measures, we're not going to be able to find our side lengths. So let's now direct our attention to item C and hope for the best. So item C, notice we're only given the fact that angle F is a right angle, therefore the triangle is a right triangle, and we know two of the sides. More importantly, we know two of the legs, EF and FD. Well, back on what we said on item 6 in the check your understanding, if we have two of the sides, we are good and have all that we need to find any unknown measures. So the first thing I'm actually going to do is find the third side, which is actually the hypotenuse of this right triangle using the Pythagorean theorem. Recall that in the Pythagorean theorem, the variable that represents the hypotenuse is C. So we're going to plug in 9 for A, 15 for B, and solve for C. 9 squared is none other than 81. 15 squared is 225 equal to C squared. We're going to combine 81 and 225 and we get 306 equal to C squared. Now, obviously, the length from E to D is not 306 units. So the last thing we need to do is solve for C by taking the square root of both sides, because the square root of a number squared is that number. Now, I believe 306 is not a perfect square. So we are going to get a decimal approximation, and they've allowed us to do that because they told us to round to the nearest 10. And I get in the calculator 17.49, so the 9 tells the 4 to round up. So the length of our third side is 17.5. Now, I do want to encourage those from here on out, if you use this measurement here at all for any of your trig ratios, your answers might just be a tenth or 100th off, as if you had used the original two side measures that they gave you. Because every time we round and then reuse that rounded measure, we're getting further and further away from our exact value. So from here on out, I encourage you to avoid using 17.5 as much as possible in your trig functions. Although you wouldn't be wrong, it's just going to be a little bit off than, say, what I would get for my final answers. So it doesn't really matter which angle you find now, because we know these two angles are going to be complementary. And so once we find one, we can subtract it from 90 degrees to find the other. So let's say we want to find angle D for Dugard. Why not? So the two measures that we were given in reference to angle D is the opposite side EF and the adjacent side FD. So the trig function that uses opposite and adjacent would be the tangent function. So in reference to angle D, we are going to use the tangent function. So the tangent of D, angle D, is the opposite side, which is FE, which we know that measure is 15, compared to the adjacent side of angle D, which is side FD, which is 9. So the tangent of angle D is 15 over 9. Therefore, the tangent inverse of 15 over 9 should give us the measure of angle D. So this is where we're using the inverse function. We're using the inverse function to find the actual angle measure. So I'm going to show you how to do that on our TI-83 and as well as Desmos. So the tangent inverse of 15 over 9. So we're going to access the inverse tangent function. So we're going to click on the second key first, tangent, and then 15 over 9, which you could reduce that to 5/3 if you want. So the tangent inverse of 15 over 9 is 59.0 or 59 degrees. I'll also show you how to do that on the Desmos calculator as well. So we're going to go to functions, tangent inverse of 15 over 9. Notice we get 59.0 again. And I also want to show you that if you reduce that fraction, 15 over 9, to 5/3, like I mentioned earlier, you still get the same value because it all stems back to similar triangles. So if we did 5/3, notice, so an equivalent fraction, because that's a ratio, and ratios that are equal are called proportions, we get the same angle measure for D. So let's go back and add that. So measure of angle D is 59 degrees. So if the measure of angle D is 59 degrees, and angle D and angle E are complementary, then 59 plus 31 is 90 degrees. Again, we could use another trig function to find the measure of angle E if we choose, and I encourage those of you that want more practice using these inverse functions, go right ahead. I'd probably use the inverse tangent function once again, because we're really trying to avoid using the length of DE, because that is a rounded measure from the Pythagorean theorem. Now let's take a look at item D and see if it is in fact solvable. And it does look like we can solve this triangle because we have one angle measure Q and one side, which we saw on item A that did in fact work. So if we know angle Q, we can go and find angle R, because again, these two angles in the right triangle are complementary. So 68 plus 22 degrees should give us 90 degrees. So now that we actually have these two angles, we could use either of these two angles to find the length of QS or the length of QR. So I guess it's really just a matter of preference here. So we'll find the length of QR, our hypotenuse, and we'll use the given angle 68 degrees. So if angle Q is our indicated angle, the length of the side we're given, SR, is opposite of angle Q, and the hypotenuse, which we're looking for, is QR. So we are going to use the sine function. The sine of angle Q, which is 68 degrees, is equal to the opposite side of angle Q, which is 58, over the hypotenuse, which we're looking for, and we will call that lowercase s. Notice opposite of vertex s, we'll call that lowercase s. So opposite of vertex r, we'll call that lowercase r. Therefore, 58 is lowercase q. It's just often how we name opposite sides of our triangle is the lowercase letter opposite of that angle. So we're calling that lowercase s. So we can, like before, get the decimal approximation of sine of 68 degrees. So we're going to jump on over to Desmos to do that. So get rid of a couple of these here. We're going to take the sine of 68. Sine of 68 degrees, just to get the decimal approximation, rounded to the nearest thousandth, which I see that the 1 is in the thousandths place. No, excuse me, the seventh is in the thousandths place. So the 1 will tell the 7 to stay where it is. So we'll round sine of 68 to 0.927. Equal to, again, 58 over s. I'll rewrite the sine of 68 as a ratio by putting it over 1 and cross multiply. So we'll get 58 equals 0.927 times s. And last but not least, we will divide both sides by 0.927. And then we will find the length of what we called side s, which my calculator tells me it's 62.567. So rounded to the nearest tenth will be 62.6. So the length of our hypotenuse is 62.6, and we don't have any units, so we could just call it units. So now that we have two sides of our right triangle, we can actually find the third side using the Pythagorean theorem if we wish, or using another trig function. So I'm going to take the opportunity to use another trig function. Why not? It's great practice of those trig functions. So we are now looking for side R, which in reference to angle Q, that's 68 degrees. That is the adjacent side of angle Q. And we were given the opposite side of angle Q. Again, I'm going to try to avoid rounded measures as much as possible. So I'm looking for the adjacent side. I was given the opposite. So we are going to use the tangent function because the definition of tangent is the opposite leg compared to the adjacent leg. So the tangent of our 68 degree angle, which is angle Q, is equal to the opposite side, 58, compared to the adjacent side, which we are calling lowercase r. Again, we're going to replace tangent of 68 with the approximated value here. So let's input the tangent of 68 and get a, that's not what I wanted to do. We have 2.475. The 5 is in the thousandths place, so 2.475. So replace tangent of 68 degrees with its approximate decimal, 2.475, equal to 58 over r. I'm going to rewrite this left-hand side as a ratio, aka a fraction, by putting it over 1 and then cross multiply to get 58 equal to 2.475 times r. Now to solve for r, because 2.475 is multiplying by r, we're going to divide both sides by 2.475. it will cancel or become the number 1 or 1r. And 58 will divide by 2.475, which I get 23.43 repeated, so roughly 23.4. Now, I encourage those that want to practice the Pythagorean theorem, now that we know it should be 23.4, feel free to utilize this opportunity to use the Pythagorean theorem to find r and make sure that it is that value that we got here. Now let's look at item 10. It says, without using a calculator, explain how you can find the value of the tangent inverse of 1. So without using a calculator, how can we find the tangent inverse of 1? So let's consider, what is it really telling us? And this is all about putting it back into context. What is it telling us if the tangent inverse is 1? And first of all, let's make sure we understand what is, when they ask how do we find the value of it, we're trying to find the angle that is associated with this ratio. So if the tangent inverse, or if the goal is to find the tangent inverse of 1, we're really looking at the tangent that is 1. So what angle, if the definition of tangent is the opposite leg over the adjacent, and here we're saying that that ratio is equal to 1, well, for a fraction to equal 1, whatever we put on the top has to be congruent to what we put on the bottom. A out of A, or 8 out of 8, or 7 out of 7. So what we're saying here, if the tangent of some angle is 1, then the length of the opposite side has to be equal to the length of the adjacent side. So let's think about the only instance that a right triangle has these two sides that are the same length. Well, if two sides are the same length, it's known as an isosceles triangle. More importantly, if two sides are the same length, then these two angles also have to be the same measure. Well, if these two angles have to sum to equal 90 degrees, and they have to be the same measure, each of these angles has to be 45 degrees. So when is the tangent of an angle 1? Well, when the length of the two legs are equal. And what type of angle, or what type of triangle has two legs that are equal? Well, it's the 45, 45, 90 special right triangle. So what is the value of the tangent inverse of 1? Well, it's 45 degrees. Because tangent of 1 is where the opposite leg and the adjacent leg are congruent. And the only instance that is true is when we have a 45, 45, 90 triangle. Now let's take a look at number 11. It says, consider rhombus ABCD, where the length of AC is 8 inches and the length of BD is 12 inches. What are the measure of the sides and angles of the rhombus? So you might be asking yourself, well, this entire lesson is all about solving triangles, nothing about a rhombus. Well, let's take a look at what a rhombus really is. So a rhombus, for the most part, what we consider a rhombus is what we call a diamond. And so that they tell us that we have this rhombus ABCD. Now, I would probably say that my drawing is a little skewed here, but we'll just base it off what they tell us. The length of AC, even though this is probably not drawn to scale, the length from A to C is 8 inches, and the length from B to D is 12 inches. In other words, they're telling us the length of our diagonals. Well, the diagonals of a rhombus actually intersect to form right angles. So what is a rhombus really made up of? It's actually made up of 4 right triangles. And you can see that I've highlighted 2 here. So we can actually find the sides and angles of the rhombus by viewing this rhombus as just 4 right triangles. So if the length from B to D is 12 inches, then from B to this intersection point is just going to be 6 inches. And if the length from A to C is 8 inches, then from C to this intersection point is going to be half of that, 4 inches. So now we are going to find the measures of this right triangle and then apply that to the rhombus. So I'm just going to pull out that right triangle just so we can view it a little bit better. So we know the length of this side is 6, the length of this side is 4, and we'll call this point where this intersection point, we'll call that X, just for the sake of clarity. So right off the bat, we should be able to find the length of this third side of the triangle, aka the outer edge of the rhombus, using the Pythagorean theorem. So I'm going to do that first. As long as we know that BC, what we're finding, is actually the hypotenuse of this right triangle, which will be lowercase c in the Pythagorean theorem. So one of the legs, which is 6 squared, plus the other leg, which is 4 squared, should equal the length of our hypotenuse squared. 6 squared is 36, 4 squared is 16, equal to c squared. 36 plus 16 should be 52. Now, hopefully we know that the length of our hypotenuse is not 52. So we now need to take the square root of both sides. Now, I don't believe that 52 is a perfect square. And it did say round to the nearest tenth, so we get away with that here. So square root of 52 rounded to the nearest tenth is approximately 7.2. So now we have the length of one of the sides. And the great thing about a rhombus is that it's a square that couldn't stand upright, really. So all 4 sides of the rhombus are actually congruent. So now we actually know all 4 sides of our rhombus. So the length of AB is equal to BC, which is equal to CD, which is equal to AD, which the length of those 4 segments is 7.2, in this case, inches. Now they want us to find the measures of the angles. Now the other property we need to discuss here of the rhombus is that opposite angles are actually congruent. So whatever we find for the measure of angle B is actually the same as angle D, and whatever we find for the measure of angle A is actually the same as angle C. So I'll go write that down here. Measure of angle A is equal to the measure of angle C, which we'll find what it is, and the measure of angle B, which is equal to the measure of angle D, and we'll find what that is. I do want to point out that not all 4 of these angles are in fact equal to each other. So how are we going to find the actual angle from the rhombus B? Well, we're going to find this part of it in the right triangle and then double it to represent the original angle we started with the rhombus. Likewise, we're going to find this angle in this right triangle C and then double it to represent this angle in the original rhombus. More than likely using a trig function or an inverse trig function, because that's what we use to find the measure of angles. So let me get rid of this work for the Pythagorean theorem. And let's find the missing angle. We'll start with B. Now, I always encourage you, again, stay away from measures that you rounded. So we're not going to utilize the hypotenuse here. We're going to use these 2 legs. In reference to angle B, this leg is the opposite leg, and this leg is the adjacent. So we're actually going to use the tangent of B here, because it compares the opposite side to the adjacent. So the tangent of B is 4 over 6. Therefore, the tangent inverse of 4 over 6 should actually get us angle B. We utilize Desmos here to find the measure of angle B. So we're going to find the tangent inverse of 4 over 6, which they tell us is 33.69, which rounded to the nearest tenth. The 9 tells us 6 to round up, so it'll be 33.7. So the measure of angle B is 33.7. Now, before you write that down here, remember we were talking about angle B in terms of this right triangle. what we need to actually do now is actually double that measure to represent the original angle that it was in the rhombus. So 33.7 doubled should be 67.4 degrees. So the measure of this angle here will be 67.4, and therefore the measure of angle D will also be 67.4 degrees. Now we can use another inverse trig function to find angle C in this right triangle, or knowing that this angle B in the right triangle is 33.7 and these two angles are complementary, we can subtract 33.7 from 90 degrees to find the measure of angle C in that right triangle. So the measure of angle C in this right triangle is 56.3 degrees. Now remember, that's only half of the original angle from the rhombus. So if we know this part is 56.3 degrees, we can double it to find the original angle, which would be 112.6 degrees, which is actually the measure of angle A and the measure of angle C. So here we have taken the opportunity to review how to use these inverse functions and the original functions to solve for right triangles. And then last, on number 11, we actually put that in the context of a rhombus, because a rhombus is made up of 4 congruent right triangles. I hope that helps solidify what we learned in the lesson. So if you need any help, let me know. There's more practice at the end of activity 22 that is always worth doing. And as always, thank you for watching.